Welcome back to the third lecture in limits, fits and tolerance. Till now we have seen how to calculate tolerance, then how to calculate allowance, then to find out what is the fit, and then later we will also what is the fit, and then we will also try to see what is the best fit available, the hole based system and shaft based system. These are the topics we have covered. Now we will try to cover some more in fits, and finally we will see the systems of limits and fits, limiting gauges and Taylor principle. So, continuing to yesterday's lecture, the next problem we will try one problem more, so that we have more clarity how to solve these problems. A clearance fit. What is a clearance fit? Where the hole size is larger than the shaft. So, the shaft can slip inside. The clearance fit has to be provided for a shaft and a bearing assembly. A shaft and a bearing assembly having a diameter of 40. So, the basic size diameter is 40. The tolerance on the hole and the shaft are 0.006 and 0.004 millimeter respectively. The tolerance are dispersed unilaterally. If an allowance of 0.002 is provided, find the limits of the size for hole and shaft when hole based system and B will be a shaft based system. We will be using L, L, H, that is nothing but lower limit of hole. We might use a terminology called as HSL. This is the higher limit of shaft. So, this is H is for hole, shaft, lower limit and higher limit. So, these acronyms will be using in problem solving. So, let us solve the problem. So, we will take a hole based system. For a hole based system, hole size is H, L, H is going to be 40.006. So, the lower level of the hole is going to be 40.000. These are all in millimeters. Okay. So, now the allowance provided, what is the allowance provided in the problem? It is 002. So, allowance provided is equal to 0.002 millimeter. Okay. So, therefore, HLS is equal to LLH minus allowance, correct. So, this is what we saw in the formula, allowance equal to this minus this we saw, right. So, when you substitute it back, we will get 40.000 minus 0.002 millimeter. So, this is nothing but 39.998 millimeter. Okay. So, now we will try to take L, H, S, that is nothing but H, L, S minus allowance, which is nothing but 39.998 minus 0.004. So, what we get is 39.994 millimeter. Okay. So, this is for the hole based system. So, let us try to solve for shaft based system. So, for a shaft B, for a shaft based system, HLS is nothing but 40.000 millimeter. So, the LLS is nothing but 40.000 minus 0.004 millimeter, which is nothing but 39.996 millimeter. Okay. The allowance here is provided is going to be plus 0.002 millimeter. So, therefore, the LLH is equal to HLS plus allowance, which is nothing but 40.000 plus 0.002 millimeter. So, this is 40.002 millimeter. So, if you wanted to express it in a pictorial form, so then it can be this is hole, this is shaft. So, here it is 39.994 and here it is 0.04. This is the 0 line and this difference is going to be 0.02 millimeter and here it is going to be 39.998 and here it is going to be 40.006. So, this difference is going to be this is going to be 40, this is going to be 40 and this is going to be 0.006 and this is going to be 39.998. Okay. This is for a hole based system. Let us draw the same for a shaft based system. This is your 0 line and 0 line. Here is your hole and here is your shaft. So, this is your shaft and this is your hole. Okay. So, now this is going to be 40.000. Okay. So, here this is going to be 40.002 and this is going to be 40.008. So, the difference is going to be 006. Okay. So, and here in the shaft based system, this is going to be 39.996 millimeter and this is going to be 0.004 millimeter. Okay. So, finally, if you want to put the closure, so the H, you have not filled up one. So, HLH is equal to 40.002 plus 0.006, which is nothing but 40.008 millimeter. So, this is important, okay, to solve it, and the rest is taken from here. So, by solving these 3 problems, to a large extent you should now have a feel for a hole based system, a shaft based system, okay, and then allowance, tolerance, maximum material condition and minimum material condition. We have to also find out the fits. So, these are the possibilities. You can expect a problem in your examination in this domain. So, let us keep moving. System on limits and fits. The rapid going of national and international trade necessitates the development of a formal system of limits and fits at the national and international level. So, today we are talking about moving parts and products, sub-assemblies from one country to another country, and assembly happens at some other country. So, if that is the case, then there has to be standards established. So, now the standards, see, we said that hole, of 0.002, 0.006. How is this 0.002, 0.006, 0.004 is decided? This is decided based upon the process which is involved in generating it. Okay. So, now what is happening? We have to now set a standard, so that by looking at the tolerance we should be able to understand, okay, what is the process which is involved, and what is a standard in one country should also be the same standard in the other countries, so that the parts manufactured can directly get into assembly. They need not undergo inspection once again. The International Organization of Standardization ISO specifies the internationally accepted system of limits and fits. Indian standards are in accordance with the ISO. The ISO system of limits and fits comprises 18 grades of fundamental tolerance to indicate the level of accuracy of the manufacturer. The ISO system provides tolerance grades from IT tolerance, international tolerance of 001, 0 to 116, okay, 16, to realize their required accuracy. So, rather than writing 0.004, 0.002, maybe there might be a typo or this or that. So, now this is replaced by a grade, which grade is IT0 some 1, or it can be ITXX. So, people will look at ITXX value and then understand, okay, this is the tolerance they have to be. So, we can avoid mistakes to realize the required accuracy. The tolerance value corresponding to the grade IT5 to IT16 are determined using a standard tolerance unit. I is in micrometers, which is a function of the basic size. So, what they say is I is this is a empirical formula 453 cube root of D plus 0.001 D in microns. So, whereas D is the diameter of the part in millimeters, right, in millimeters. The line a linear factor is nothing but 0.001 D is a linear factor which is counteracted, this is a linear factor which is counteracted. The effect of measuring inaccuracies is taken care by this. So, the tolerance grade values to grades IT5 to 16 can be determined by using this formula. So, you try to find out what is the grade. D is the geometric mean of lower and upper diameter of a particular diameter step within which the given or the chosen D lies, and is calculated by using the formula D max into D min by root. The various steps specified for the diameter are as follows: 1 to 3, 3 to 6, 10 to 6 to 10, 10 to 18, and it goes on from 800 to this. So, we can try to take the maximum, minimum, try to take a root and then go back for this D and use it in this D to get the I. So, the tolerance have a parabolic relationship with the size of a product. So, this relationship is very, very important, and these D's max and min are these D's which are given in the step. The tolerance within which a part can be manufactured also increases as the size increases. Please understand that what are we trying to say? Tolerance T increases or is directly proportional to size increase. As and when the size increases, the tolerance also increases. The standard tolerance corresponding to IT was 01, IT 0 and IT 1 are calculated using the formulae. IT 01 is nothing but 0.3 times plus 0.008 D. So, these are formulas which are available in the handbooks. So, what are we trying to do is we are trying to find out the tolerances given for this IT. So, if you look at the ISO system defining 28 classes of basic deviation for hole based system and for shaft based system. So, this is for a hole and this is for a shaft. This is for a shaft. The bottom whatever is there is for a shaft and this is for a hole. So, here is the 0 line. So, it is basic line, 0 line, okay, and here you can see the fundamental deviations. So, here the deviations of the hole and shaft which are marked by capital letters A, B, C to ZC, with the exception of I, L, O, Q and W, are the smallest letters A, B, C to ZC, with the exception of I, L, O, Q. So, these are different ways of the alphabets are given. So, what happens is, now when you have to choose a clearance fit or interference fit or transition fit. So, then what happens is, we try to choose the shaft, what is the letter, and corresponding to it we chose, this is a hole, this is a shaft we choose, and based on this we try to talk about the clearance fit. So, this is for transition and this is for, suppose you take E and you say Z. So, it is a interference fit. Okay. So, this is what we are trying to say. The ISO system defines 28 class of basic deviation for hole and shaft based system. With this, what we can do is, we can try to figure out what should be the tolerances which are given for the hole and for the shaft to have the necessary fit. The values of ES and EI are for the hole and value of ES and EI are for the shaft, can be determined by adding and subtracting the fundamental tolerance respectively. So, what we are trying to say is, you take a 0 line, okay, then you try to take this is your ES and this is your EI. Okay. This is for a deviations for A to G. Okay. And if you try to take this is your 0 line, okay, this is your ES and this is your EI. This is for deviations for K to Z. It will be like this. Next, if you want to have for the other one, so this is your 0 line, this is your 0 line, this is your ES and this is your EI, and this is for deviation for A to G. This is for a shaft based system. Then you will have your 0 line, this is your EI and this is your ES. This is for deviations for K to Z. This is K to Z, small k to Z. Okay. This is for a shaft. So, this is for a hole and this is for a shaft. So, the values of ES and EI for a hole can be expressed from A to G, can be expressed like this. So, this is your deviations. This is your hole based deviations, right. So, let us try to solve one simple problem. Design the general type of go to no go gauge as per the British system for a shaft of 40 millimeter and a hole pair designated as 40 H8, H8 and D9 given that I equal to 0.453 cube root of D plus 0.001 of D. This is linear factor. So, there are several divisions given. So, let us try to solve each subdivision and try to get the answer. So, let me first try to draw the figure. This is going to be your 0 line, maximum hole size, maximum hole size. This is going to be your hole tolerance. Okay. This is for a not go gauge. We will see go gauge and not go gauge little in detail, but as of now we will see only the tolerances part of it. So, then you will have corresponding gauge tolerance. This is your basic size. This deviation is the wear allowance. This is your fundamental deviation. This is for minimum of shaft size. Okay. This is the shaft tolerance. This is your gauge. This is your gauge tolerance. Okay. And this is your not go gauge. Okay. And this is your fundamental deviation. Fundamental deviation, and this and this space, if I try to take these two, are going to be the wear allowance. This is the minimum hole size, and this is minimum. So, this is a hole size, and this will be the minimum of the hole, and this is a minimum of the. So, here it will be minimum hole size, and this will be maximum shaft size. So, this will be maximum shaft size. Okay. So, this is the pictorial representation of whatever we have understood till now. So, we have put all those things here. So, now next we will try to solve the problem. So, first let us solution. First, what we have a standard diameter step for 40 millimeter, and this 40 millimeter falls in range of what? 30 to 50. Okay. So, when we have to calculate D, can be calculated from the formula root of D max into D min. Okay. So, this is approximately equal to 38.7298 millimeter approximately. The value of fundamental tolerance is I equal to 0, formula given 0.453 cube root of D plus 0.001 D. So, which is approximately, which is nothing but 0.453 cube root of D, which is 38.7298 plus 0.001 into 38.7298, which is equal to 1.571 microns. Okay, we have calculated the I from the D is also given. Now let us get into for hole quality, what they have said, H8. Okay, H8, the fundamental tolerance is nothing but is 25I. If you go back, 8 is I, which is given in the this thing formula. So, it is 25I. So, it is 25I equal to 25 into 1.571, which is nothing but 39.275 microns. Okay, or it can be said as 0.039 millimeter. Okay, for a hole, the fundamental deviation is 0. Okay, so hole limits are going to be, the hole limits are L, L, H. Lower limit for hole is going to be 40.000 millimeter, and the higher limit of hole is going to be 40.000 plus 0.03 millimeter, which is nothing but 40.039 millimeter. Okay. So, the hole tolerance is going to be 0.039 millimeter. Okay. Now, let us go for a shaft. Now, for a shaft. For a shaft quality, shaft is small capital D9, the fundamental tolerance is, so we have 40I, which is nothing but 40 into 1.571, which is 62.84 microns, or which is nothing, which can be written as 0.062 millimeter. So, the fundamental tolerance is 40I, which is also given in the problem, by the way. It is also given in the problem, 40I, right? Is 0.62, 62 or 63 we will make it, 63, because it is very close, 63 we will make it. Okay. So, now for shaft, the fundamental deviations is given by what? Minus 16d to the power 0.44. Okay. So, where is this coming from? E, upper deviation of the shaft. Okay. So, this is E. Okay, this is E, this is D. Okay, this is also given. So, the fundamental deviation deviation is nothing but minus 16 into D, which is 38.729 to the 0.44. Okay. So, where did this 38.729 come from? 38.729. This is 38.729 came from here, D max minus T. So, this is the D we get, and we have substituted in the problem. So, minus this. So, this is nothing but minus 79.956 millimeters approximately. Okay. So, no, it is microns. It has to be in microns. So, if I want to convert into millimeter, it is going to be minus 0.80 minus 0.080 millimeter. Hence, the shaft limits are as follows. What are they? They are shaft is nothing but 40.000 minus 0.080, which is 39.92 millimeter. Then for lower level of the shaft is going to be 40.000 minus 0.08 plus 0.063, which is equal to 39.857 millimeter. Now, the shaft tolerance is going to be 39.92 minus 39.857 millimeter, which is approximately 0.063 millimeter. So, the hole and shaft limits are 40 plus 0.039 plus 000 and 40 minus 0.080 and minus 0.143 millimeter. Okay. If you want this to be represented into a figure form, then let us draw the figure. So, it is like this. You have a 0 line, this is your 0 line. Okay. This is 40 millim 40. Okay. Then you will have a hole, this is your hole, and this is your shaft, and here the 0.08 will be the fundamental deviation. Okay. Here it will be, and this difference is 0.063 and this difference is going to be 0.039. So, the value here is going to be 40.039 and this is 40, which we have already told, and here it is going to be 39.92 and here it is going to be 39.857 millimeter. Okay. So, this is a fundamental deviation. This is nothing but the higher limit of hole, this is lower limit of hole, this is going to be the higher limit of shaft and this is going to be the lower limit of shaft. Okay. So, now the last part of the question is going to be what should be the wear and tear, which is given as of 10%. Okay. So, let us see some of the terminologies which are used in tolerances. Basic size, is the size in relation to which all limits of size are derived. So, 40 plus or minus, that 40 is the basic size. Basic size or nominal size is the same, is defined as the size based on which the dimensional deviations are given. This is in general the same for both components. What are the limits of size? There are two limits, maximum and minimum permissible size acceptable for a specific dimension. The operator is expected to manufacture within the maximum and minimum limits. Within these limits, the maximum limit of size is greater of the two limits of size, whereas the minimum limit size is the smaller of the two. What is tolerance? The tolerance is the total permissible variation in the size of dimension. For example, 40 plus or minus 0.2 we say. So, that is what. So, the difference between the maximum and the minimum limits of size is nothing but the tolerance. So, limit of size, maximum and minimum, within that they have to do. Tolerance is the difference between maximum material and minimum material. Allowance is the next important thing. It is the intentional difference between lower limit of hole and higher limit of shaft. And allowance can be either positive or negative. The allowance, this is the formula which is used, very important. Then we talk about grade. It is an indication of the tolerance magnitude, IT 6. So, it is the 6 talks about the magnitude. Lower the grade, finer the tolerance. For example, if we talk about IT 1, we compare it to IT 16. IT 1 has a tighter tolerance or a lesser tolerance. Deviation, it is the algebraic difference between the size and its corresponding basic size, between a size and its corresponding basic size. It may be positive, it may be negative, or it may be 0. So, these deviations are the ABCD which we saw for a hole based system and for a shaft based system. Upper deviation, it is the algebraic difference between the maximum limit of the size and the corresponding basic size. It is designated as ES for a hole and ES for a shaft. Okay. When we talk about upper, there should be naturally a lower limit also. So, they are in turn talked as EI for the minimum limit for the hole and EI for the shaft. These are the deviations. So, please try to understand deviation. It is the algebraic difference between a size and its corresponding basic size is the deviation. So, upper, lower. What is actual deviation? It is the algebraic difference between the actual size and its corresponding basic size is the actual deviation. Then we talk about fundamental deviation. It is the minimum difference between the size of a component and its basic size is called as fundamental deviation. This is identical to the upper deviation for a shaft and a lower deviation for a hole. So, this definition is also very important. Zero line, the line is known as a line of zero deviation. The convention is to draw a zero line horizontal with positive deviation represented above and the negative deviation represented below. A shaft and a hole, these are terms which are used to designate all the external and internal features of any shape and not necessarily cylindrical. Okay. So, these are some of the terminologies which we have been going through in this chapter. Fits. Fits, it is the relationship that exists between two mating parts, a hole and a shaft. Clearance fit, transition fit, interference fit. Maximum material condition, this is the maximum limit of an external feature. For example, a shaft measured to its high limits which will contain the maximum amount of metal. Least metal condition is the minimum limit of an external feature. For example, a shaft will contain minimum amount of material when the manufacture to its lower limit. Tolerance zone, the tolerance zone that is bound by the two limits of size of the compound are called as tolerance zone. It refers to the relationship between the relationship of tolerance to basic size. So, then it is international tolerance grade. Tolerance grade are indicated of the degree of accuracy of manufacturing. It is used for international, so that it can be produced from one place and it can be moved to the other. Then tolerance class, it is designated by the letters representing the fundamental deviation, followed by the number representing its standard tolerance grade. So, for example, it is IT is the tolerance grade, the letter IT are omitted and the class is represented as H8 F6. You can represent, see, when the tolerance grade is associated with a letter representing a fundamental deviation to form a tolerance class, the letters IT are omitted and we directly write H8 and F7. So, here it is IT7 is international tolerance grade, tolerance class is H8 F6. Then tolerance symbol is going to be, there are specific tolerance and fits for a mating component. For example, it will be represented like this. This is the basic size, this is the hole deviation, this is the shaft deviation. 40 indicates the basic size, H indicates the fundamental deviation of a hole, F indicates the fundamental deviation of a shaft. This 8 and 7 is what we are trying to get the class, and this can be calculated by the formula which we used in solving it. The last topic of discussion is going to be the limiting gauges. Limit gauges ensures the component lie within the permissible limit, but they do not determine the actual size or dimensions. For example, I try to have a gauge which only checks whether the dimension is okay or not okay. So, gauges are scale-less inspection tools. So, here it is only yes, no, which are used to check the conformance of a part along with their form and the relative positions of the surface of a part to the limit. The gauge requires to check the dimension of a component corresponding to two sizes conforming to the maximum and minimum limit. So, whatever we say maximum material maximum condition, minimum condition, whether the component falls within that and whether it is okay or not okay. We do not measure the actual size. The limit gauge, there are two types of gauge, they are called as go gauge or no go gauge or not go gauge. So, if you try to take a hole, this is a hole, this is the tolerance of on hole. Okay. This is the maximum material limit. This is the tolerance of the hole. This is a go gauge. Okay. This is no go gauge, and this is the lower material limit. So, this is for a metal, limits for hole gauging. So, we can also have a same for shaft. So, here not go gauge, this will be your go gauge. is tolerance on shaft, okay. This is your maximum material limit and this is your lower material limit. This is for a metal limits for shaft gauging. Thank you.